All right, class, settle in. Today, we're going to pull back the curtain and look at the secret social lives of atoms. Yeah, you heard me. We're talking about how they interact, what they're looking for, and the pretty dramatic ways they get what they want.
So let's start with something you absolutely have in your kitchen, table salt. Have you ever really thought about it? Like why it forms those tiny, hard crystals? Or why it just seems to vanish when you stir it into water? Well, the answer to all of that lies in the powerful forces holding its atoms together.
You see, at its core, this whole thing is a story about a chemical bond. And today, we're zooming in on one of the most dramatic types out there, the ionic bond. Let's get into it. To really get why atoms bond, you have to understand their one single universal goal. It's kind of like us, really. Atoms are on this constant quest for stability. An unstable atom is super reactive, but a stable one, it's just content, chilling.
So what's the ultimate status symbol for an atom? A full outer shell of electrons. And for most atoms, that magic number is 8. This drive is so important, so fundamental, that it has its own name, the octet rule. You could call it the rule to rule them all in the world of chemical bonding.
Now, some atoms are already in the stable club. These are the noble gases. They're the cool kids of the periodic table. Their outer shells are already totally full, so they don't really need to bond with anyone. They are the role models every other element is trying to be like. So what do you do if you're not a noble gas? How do you get that full outer shell? Simple, you form a bond. And in the world of ionic bonds, we've got two main players with completely different strategies for getting there. On one side, you have the metals. They've only got 1 or 2 electrons in their outer shell. For them, it's way easier to just give those away to get to that full shell hiding underneath. And on the other side, we have the nonmetals. They are so close to having a full shell, they just need 1 or 2 more. They are very aggressive electron takers.
We can actually measure how willing an atom is to give up an electron. It's called ionization energy. You can think of it like the price to remove an electron. For metals, that price is super low. It takes almost no energy to just pluck one of their electrons away, which is exactly why they're such great givers.
And on the flip side, we can measure how much an atom wants to gain an electron. That's called electron affinity. Now, nonmetals have a really high affinity. In fact, when they grab an electron, they become so much more stable that they actually release energy. That's how badly they want it. Okay, so you've got a generous giver, and you've got an eager taker. What do you think happens when they finally meet? That's right, the main event, a great electron transfer. Let's go back to our friend, table salt, sodium chloride, to see exactly how this goes down.
Let's walk through this. Sodium, a metal, is happy to give away its one lonely outer electron. Chlorine, a nonmetal that's just one short of a full set, snatches it right up. Now, think about the charges. Sodium just lost a negative electron, so it becomes a positive ion. And chlorine just gained one, so it becomes a negative ion. And what do opposites do? They attract. Bam! They are now powerfully bonded to each other.
So here's the crucial point. An ionic bond isn't like glue or some kind of physical string holding these atoms together. Nope, it's a force, a powerful, invisible force of attraction between the brand new positive and negative ions. We call it electrostatic attraction, and believe me, it is incredibly strong.
Okay, so now that we've seen a simple one-to-one transfer, let's check out how this works with some other compounds. The goal is always the same. Atoms are going to transfer electrons in a way that creates a new, stable compound that has an overall neutral charge. It's all about that perfect balance.
Let's look at calcium and oxygen. Calcium is a metal and it's got 2 outer electrons it wants to give away. Oxygen is a nonmetal, and it needs exactly 2 to complete its octet. I mean, come on, it's a perfect match. Calcium gives 2, oxygen takes 2. Calcium becomes a +2 ion, oxygen becomes a -2 ion. And those charges cancel each other out perfectly to form the very stable compound calcium oxide.
But what happens when it's not a perfect one-to-one match? Let's take magnesium, for example. It's got 2 electrons it absolutely needs to get rid of to be stable.
So, magnesium finds a great partner in chlorine, but there's a little problem. Chlorine only has room to accept 1 of those electrons. It can't take both. So magnesium gives away 1 electron to a chlorine atom, but it's still stuck with this extra 1 it needs to lose. So what's a magnesium atom supposed to do? Oh, it's simple. It just recruits a second chlorine atom to the party.
Magnesium gives its first electron to one chlorine, and its second electron to another chlorine. Now its +2 charge is perfectly balanced out by two separate chlorine ions, each with a -1 charge. The final compound, MgCl2, is stable and perfectly neutral. Problem solved.
Okay, so these atoms have successfully transferred electrons, they've formed these super powerful bonds, but what does that actually mean for the compounds they create? What's their life like now that they're all bonded up?
Well, because that electrostatic attraction is so strong and pulls in all directions, these ions pack themselves together into these tight, organized, three-dimensional structures we call crystal lattices. This structure makes them really hard, but also brittle, kind of like glass. It also takes a ton of energy to break those bonds apart, which is why they have such crazy high melting and boiling points.
Now, this last point is really cool. In their solid crystal form, those ions are totally locked in place. They can't move, so they can't conduct electricity. But when you dissolve an ionic compound in water, the water molecules actually surround the ions and pull them apart. We call this process dissociation. And once those charged ions are free to move around and swim in the water, they can carry an electrical current.
So this dramatic transfer of electrons, this whole give and take, it's the foundation for the entire world of ionic compounds. But here's the thing, it's not the only way atoms can get stable, which leaves us with one last question to chew on. What happens when a nonmetal meets another nonmetal, and neither one is willing to give up its electrons? What happens when they have to learn to share? We'll dive into that next time.